Hi, everyone. Welcome back. Today, we're going to talk about Chapter 8. In this chapter, we're going to talk about a unique type of mixture called solutions. Okay, not only will we introduce what are solutions, but also we're going to do some calculation about solutions. Okay, here is, as usual, the chapter guidelines showing in the first part, we're going to talk about what are solutions and what are the rules for something to be soluble into another. And then the second part, we're going to talk about the concentrations of solutions, including different types of concentration units. And then finally, we're going to talk about some unique properties of solutions, okay, especially colligative property. Okay, so let's get started. What are solutions? In order to study solution, we have to review a concept we learned in chapter 1. If you guys can pause, or if you want to follow me up here, we know matters are classified into two types by composition. One type is called a pure substance, means only one substance. Another type is called mixture. Mixture is a physical combination of what? Two or more substances. Means those substances can coexist without any chemical reaction, called a physical combination. And then we also further classify this mixture into two types based on the appearance. If the mixture shows different visible phases, such as water and oil, or sand and water, or mud, like these, they have different phases, not a uniform. We call those mixtures heterogeneous mixture. If a mixture shows uniform property throughout one visible phase, like your tea, perfume, and Gatorade, these are called homogeneous mixtures, right? If you learn these two concepts, different types of mixtures, then you will have no problem understanding what solutions are. Because solution is a homogeneous mixture. Or a homogeneous mixture, you can call it a solution. So what does it mean? It means a solution is a mixture in which two or more substances physically combined, and the whole thing appears to be a uniform phase, and the whole mixture has uniform property throughout. That is called a solution. Now, since we're learning solution now, we have to give the components of that mixture their names. The component that exists in greater amount, we call it the solvent of the solution. The components that exist in minor amount or amounts, depends on other components, how many components there are, we call them solute or solutes. So usually you have a solvent that is the greatest amount, and then you have one or more solutes, depends on how many components you have in the mixed solution. Solutes are the one that in smaller amount. And after we understand what solution is, here we have some very easily understandable but great summaries about what would you expect for a solution, so that you have a fully understand the overall picture of what solution is. Okay, the first one is solution should have two or more components, a solvent and one or more solute. Number two, solution has a variable composition. Okay, this one I want to briefly talk a little more. What is variable composition? It means a solution will be different from another solution, even though you're talking about the same solution. tea. One cup of tea will be different from another cup. That's the nature of a mixture, a variable composition. A cup of coffee will be different from another cup, even made by the same person. Number 3, change, property change as the ratio of the solute and solvent change. So if you change the amount of different components, the property of the solution will also change. Number 4, the solute dissolves in the solvent as individual particles. The particle can be molecules or atoms or ions. Number 5, the solute remained uniformly distributed throughout the solution, will not settle with time, because again, it's uniform phase. It will not settle. You put the solution over there for a long time, it will not settle, because the particles are evenly distributed. Number 6, you can actually separate the components by physical means. Okay, physical means what? Means you don't have need a chemical reaction. You can use physical means to separate the component, such as, for example, salt and water dissolved in water. You can separate the salt and water by what? By evaporation. If you evaporate all the water, you have salt in the end, get left behind. Because solution is a physical combination of different components. And then that means you can physically separate them, use physical method without a chemical reaction. So hope these properties will give you, again, some of them I'm talking about already, but these properties will give you a better picture about what solutions are. Now, since we're talking about solution, we want to briefly mention another type of a homogeneous mixture that is slightly different from solution, but also sometimes might confuse us or hard to tell, called colloidal dispersion or colloids. Colloids is different from solution is because the particles that are dispersed in the solvent is slightly bigger than particles in a solution. Okay, solution. But because the particles in colloids are still evenly distributed, or we should call them dispersed. Okay, dispersed. They still won't settle. The particles won't settle. But instead of dissolved, they're just suspended, like dispersed, and the size is bigger. The best example of a colloids is a glass of milk. It's actually not a solution, because the particles in milk, like proteins mostly, lipids, proteins, their sizes are actually bigger than usually we consider in solutions dissolved molecules or atoms or ions. The protein molecules are regularly bigger. But again, unless the milk goes bad, the particles in milk will not settle. You still see it kind of like uniform. And these are called colloids. Now, of course, someone will ask, how do we tell the difference between colloids and solutions? There's a very famous experiment called the Tyndall effect. Colloids, they have Tyndall effect. That is, if you shine a beam of light through a solution versus a colloidal dispersion, the track of light cannot be seen in solution, but the track of light can be seen in colloids, because the particles in colloids are bigger, so they scatter lights. That's why you can see the passage, the track of light. And that is called the Tyndall effect. That will tell you, hey, that mixture is not a solution, but a colloid. If you see Tyndall effect, the light passage of light. Okay, this is another life experience For Tyndall effect, when sunlight enters the dense forest, you can see the beam of light. That is actually Tyndall effect, because in the morning, the moisture air, some tiny particles, dust suspended or dispersed in the air, scatter lights. So in the morning, the air is actually a colloidal dispersion. Dense air, a dense moist air. Okay, it's just one brief, some info about, but again, mostly homogeneous mixtures are solutions. Okay, only if the particles are slightly bigger, we classify them as colloidal dispersions, especially if they have Tyndall effect. Now, let's go back to solutions. Because solution contains some solute, one solute or more solutes dissolved in a solvent. So we care about the maximum amount of solute that can be dissolved in a given amount of solvent under a given set of conditions. Like you have a certain amount of solvent and also temperature, etc. The given set of conditions, we care about, hey, how much that solute can dissolve. And that is called the solubility of the solute. Okay, how much maximally you can dissolve. Speaking of solubility, there are two important trends. One trend is solid will usually be more soluble in water when the temperature is higher. Increased temperature, you can increase the solubility of solids, but it's opposite for gas. That means increase the temperature of water, the solubility of gas is going to decrease. You're going to kick the gas out if you increase the temperature. Okay, that's one very useful trend. You can see this is the table showing you the solubility of some solids versus temperature. You can see that for most solids, there are exceptions, but most solids, their solubility increases if the temperature increases. See that? These are some ionic compounds, the solids. Their solubility increases as the temperature increases. But for gas, it's opposite, remember. Solubility decreases as you increase the temperature. That's one useful trend about the solubility. Another trend is pressure. Okay, pressure doesn't have much effect on the solubility of solid and liquid, but pressure has major effect on the solubility of gas. Okay, pressure normally doesn't affect solid or liquid in water. It affects gas. That is higher pressure, greater solubility. Lower pressure, smaller solubility. That's what we call here directly proportional. Means what? Higher pressure, the gas will be more soluble in water. Lower pressure, the gas will be less soluble. So you see that we talk about, basically we talk about what the condition, temperature and pressure, how they affect the solubility of liquid, solid, and gas. Next, when a solution has the maximum amount of solute dissolved under that condition, we call the solution a saturated solution. It has the maximum amount of solute already dissolved. We call that saturated. Now, someone wanted, how would I know if a solution contains the maximum amount of solute dissolved? A saturated solution will look like this. That's how you know. That is, you even have some undissolved solid shown. That means what? means the solution already dissolved the maximum amount. Okay, you have some undissolved solute showing up. That means the solution is saturated. Now, even though you have some solid showing up, this solution formation is still happening. That means the particle is still breaking up into solution. But meanwhile, the particles in solution is actually kicking back to the solid. So you don't see the solid increase or decrease anymore in a saturated solution. But the solution particles, the solute particles still goes into the solution, and solution particles, the solute particles in solution still kick back to the solid. And we call that process, again, a physical equilibrium, okay, or dynamic equilibrium. It means that both the direction is still happening. Particles breaking apart and particles coming back. But when we see it, we saw the amount of the solid or undissolved solute doesn't change. That's called equilibrium. And again, we know that the solution has already contained the maximum amount of solute. We call that saturated. The saturation sometimes can go above the maximum amount. That is, a solution can actually dissolve more than the maximum amount, or more than that is normally in a saturated solution can dissolve. But that stage is not a stable stage. That solution is not a stable solution. And we call that solution a supersaturated solution, like this one. They actually dissolved more solute than in a saturated solution. And the reason we call it unstable, because it dissolves more than it should. And when there is some little disturbance, like you put a glass rod in it, or maybe you touched it with your hand, the excess amount of solute will crystallize out very fast. And the solution will revert back to saturated. Okay, the solution will pop out very quick. The solute will pop out real quick. And the solution now goes back to what? A saturated solution. Okay, supersaturation is one unstable stage, just to point it out. Next, when you dissolve something into a solvent to form a solution, there are three things to consider to help you to make a solution easier if you consider these three things. We call the factors affecting the rate of solution formation. First is the solute particle subdivision will affect it. Smaller the solute, better divided the solute will dissolve better because it has greater surface area. How do we understand this? If you wanted to dissolve some sugar in water, a big chunk of sugar or tiny sugar fine powder, which one dissolves faster? Of course, the fine powder dissolves faster because fine powder has greater subdivision, greater surface area, dissolves faster because better contact of the solute with the solvent to break them apart. That's the first factor to consider when you form a solution. Second factor is also something easy to understand, that is agitation, degree of agitation during the solution preparation. If you agitate, such as stirring, can increase the dissolution process, increase the solution formation, right? When you dissolve sugar in water, you want to stir it while you're adding sugar because that will help the sugar to dissolve faster. Number three, the temperature of solution formation. Higher temperature the solid particles can break down rapidly, more rapidly, because of higher kinetic energy. So you can make a solution faster. Just like you're making sweet tea, you need to make sure tea is hot while adding sugar, because you can dissolve more sugar when the solution is hot. And also, higher temperature will help sugar to dissolve faster and easier. So these three factors, subdivision of the solute, agitation, and also higher temperature, will affect the rate of solution formation. Next, when you make a solution, we know how to make it faster, but how do we know in general a substance will dissolve in another solvent, for example? How do we determine if the substance will dissolve with each other? And we're going to study the rules helping us to determine, called solubility rules. Okay, the rule for solubility is generally simple for most substances, because the rule contains only 3 words: like dissolves like. Okay, what is like dissolves like? Like dissolves like means a polar substance will most likely dissolve in a polar solvent. A non-polar substance will most dissolve in a non-polar solvent. Like dissolves like. Substances of like polarity tends to be more soluble in each other than substances that differ in polarity. Okay, the same way of explaining is polar substance dissolving polar solvent, such as water is a polar solvent. Then water tend to dissolve in polar solute. Non-polar solvent, for example, gasoline, tend to dissolve non-polar solute. And polar solute don't dissolve in non-polar solvent, vice versa. Like dissolves like. A very important empirical rule called like dissolves like. But this rule is very useful in predicting solubility of gas in liquid, liquid in liquid, and solid in liquid, except the solute is ionic. It is applied in most cases: gas in solid, liquid, gas in liquid, liquid in liquid, and solid in liquid. Okay, they can predict unless the solid is ionic. That the rule normally doesn't apply. Okay, the solute, when it is solid, cannot be ionic compound to apply this rule. That is something different we need to learn. But otherwise, the rule called empirical rule of like dissolves like very well predict the solubility between different substances. Quick practice. Greater difference in solute-solvent polarity will result in what? Smaller solubility, because the difference is big means what? They don't like each other. They don't like each other means the solubility will be what? Low, less solubility of the solvent. That's like dissolves like. Now, like we said, the rule applies for the solubility of predicting the solubility of most cases, except when the solute is ionic compound. So here we're going to learn a separate rule that can predict the solubility of ionic compounds. Okay, of ionic compounds. And that rule are shown in this page and next page, which is a table from a book. Okay, I hope you can commit these rules to your memory because they will be very useful to predict ionic compound solubility. The rule contains two parts. The first part, we're talking about soluble ionic compounds. Remember, ionic compounds are what? Are compounds containing ions. Okay, that's something you should refer to chapter 4. Okay, we're talking about ionic compounds. What are ionic compounds? As a positive ion and a negative ion. Okay, we can even write the formula of ionic compounds. Okay, hope you still remember what we learned about chapter 4 ionic compounds. And here we're talking about how do we predict the solubility of ionic compounds, of course, in water. Okay, in water. The first rule, again, applies for soluble ionic compounds, meaning what we're talking about here, most of them are soluble. For example, nitrates and acetates. If a component containing these two ions are mostly soluble. Compounds containing alkali metal, lithium, potassium, sodium, and ammonium ions are also soluble. Okay, also soluble. Number 3, halides means compounds containing chlorine, bromine, iodine. These ions are mostly soluble except, you can see now they have exceptions, except when they are pairing with lead, zinc, silver, and mercury. Okay, that means what? Silver chloride is not soluble because silver is an exception for chloride. Most chlorides are soluble. Okay, again, this is how you understand these. Number 4, sulfates are mostly soluble except with strontium, barium, lead, and mercury. Means barium sulfate is not soluble, even though sulfates are mostly soluble. And here I put calcium sulfate. Usually we assume it is soluble, but it's actually slightly soluble, but still we assume it is soluble. Okay, the exception for sulfates is strontium, barium, lead, and mercury. So that is the group of soluble ionic compounds in the first part. Again, chlorides, bromides, iodide, and sulfate, they have exceptions. The first two, nitrate, acetate, lithium, sodium, potassium, ammonium, they don't have exceptions. The second part of this rule are ionic compounds that are generally insoluble. That means not soluble. First, carbonate, phosphate are normally not soluble except when they have something we mentioned in first part, when they have lithium, sodium, potassium, or ammonium ions. Remember, we know these guys are not always soluble. So these are exceptions for carbonate and phosphate. Okay, if you have one of the soluble ions, then they will be soluble. Otherwise, carbonate, phosphate are normally not soluble. The second one, hydroxide are not soluble except with lithium, sodium, potassium. Again, alkaline metals. Because alkaline metals containing compounds are soluble, remember? So there are exceptions for hydroxides that are not soluble. Number 3, sulfides are not soluble except with alkali metal, with calcium, with ammonium. Again, alkali metal ammoniums are always soluble, so there are the exceptions of calcium. And calcium sulfide, is also soluble. Also an exception for sulfate. So you see that each rule are talking about either soluble or insoluble compound with some exceptions. And soluble ones, especially lithium, potassium, Sodium or ammonium cations are exceptions for those that are not soluble, for insoluble ones in part 2. Okay, I know some of you still maybe a little confused of how to use these rules. Okay, we have some practice for you. I will explain going back and forth. Okay, this is the one from your book. The same thing, 2 parts, listing soluble ones or insoluble ones with exceptions, what their exceptions are. Okay, you can use either one. They're the same. But let's take a look at some practice and use these rules and show you how to use these rules. Okay, the first practice is, which of the following ions that are generally soluble in water with lead? Okay, with lead. We know lead normally, take a look, for soluble ones, lead are even exceptions. See that? The soluble ones are on top. And lead are exceptions. Okay, exceptions. So if you want a lead and still be soluble, you need something that is always soluble, which is what? Which is nitrate. Because nitrate, see that? Here's nitrate, is always soluble, no exceptions. So when lead meets light nitrate, it's still soluble, even though lead makes exceptions for soluble all the time, but nitrate is always soluble. In fact, lead 2 nitrates is actually soluble. Next, there are 10 compounds showing here, asking you to determine the solubility in water. Only 2 answers, either soluble or insoluble. Right? Let's take a look at all of them. The first one is lead chloride. Okay, lead chloride. We know lead chloride. If you look at chloride, chloride belongs to soluble compound, but lead is an exception. So lead chloride is what? Is not soluble. No. Potassium hydroxide, second one. Okay, potassium hydroxide. Let's go back. Hydroxide are what? Not soluble, insoluble, but exception with group 1A, potassium. So potassium will make what? Hydroxide soluble. So yes. Okay, yes. Number 3, magnesium sulfate. We know sulfate belongs to what? Soluble. Magnesium is not one of the exceptions. You see, the exception doesn't contain magnesium. So what? Magnesium is soluble. Now, I'm not going back and forth all the time. I'm going to briefly talk about why it's soluble or not. Okay, hopefully you can pause the video and go back and double check. Okay, because I memorized the rules already. Next, calcium carbonate. Carbonate is normally insoluble. Calcium is not an exception. Calcium is not an alkali metal. So calcium carbonate is not soluble. Mercury 1 chloride. Chloride is soluble, but mercury is an exception. So mercury chloride is not soluble. Okay, mercury chloride is not soluble. No. Potassium sulfate. I'm sorry, potassium sulfide. Sulfide is not soluble, but potassium is the alkali metal, so it's an exception. So potassium sulfide is soluble because of the potassium. Next, lead 2 acetate. Acetate is always soluble, no exceptions. Yes. Magnesium hydroxide. Hydroxide is not soluble unless with what? With alkali metals or ammonia. Magnesium is not one of them. So magnesium hydroxide, not soluble. Barium sulfate. Sulfate is normally soluble, but barium is an exception. So barium sulfate, not soluble. Ammonium carbonate. Ammonium salts are always soluble. Calcium chloride. Chlorides are mostly soluble. Calcium is not an exception, so yes. And finally, copper sulfate. Sulfate is not soluble. copper is not an exception. So no. All right. No. Okay, of course, yes means soluble. No means, oops, this. Yes means soluble. No means insoluble, right? Okay, you can study them from top to bottom or side-by-side comparison. You can see that side-by-side, you can compare them. No, yes, yes, no, no, yes, yes. But again, make sure you can use this chart to predict the solubility of ionic compounds, and then use like dissolves like to predict the solubility of compounds other than that. Okay, other than that. So I'm gonna stop here, call it part L1, and in part 2, we're gonna keep moving on, talking about the concentration of solutions. That is, how much solute is dissolved in a certain amount of solution, called a concentration. And I'll see you in part 2.